Well, I'd like to thank the organizers for inviting me. I decided to give the lecture on the board in a hope that even though I may cover less, maybe I'll hope to uncover more by going a bit slower. And also for the benefit of the students in the audience, I'll see how much I will cover, and if I won't succeed to cover all, that's fine. So the title of the workshop has the word generalized in it. So let me give you two examples of generalized symmetries. One of them is the example of what goes under the name of the higher form symmetries. And I think Michal pointed out that he's going to talk about this tomorrow. It briefly featured in Vijay Shanoy's presentation when he talked about the toric code. Remember, there was the idea that you could define an operator defined on some Wilson line, where you take a product for all I that depends on this Wilson line, and you take some operators O over that. And then the idea is that that symmetry is defined on some topological line, may not be distorted. And the dimensionality of this manifold here determines the symmetry. So the regular symmetries we're used to are defined on site. So this is a zero form symmetry. Something like this that's defined on a line would be a one form symmetry. And you saw examples of this when you look at the toric code. So the logical operators, you could call them X, W, would be something like a product of X on an inconstructible loop of a torus, right? So the example was that if I consider a torus, and if I look, for instance, over this loop W over here, that this would be example of the operator. Now you could show that this operator commutes with the Hamiltonian, so it's a symmetry. And then the way we understand now what classifies the topological phase of matter is that this symmetry gets spontaneously broken. So the idea is that the topological order corresponds to spontaneously broken, in this case, one form symmetry. Okay? And I hope that we'll hear more about this from one of the speakers tomorrow. Now, the other aspect, so this, by the way, dates back to roughly about 2014. So it's not such a long time ago. Another development, which is a bit harder to put the exact date on it, concerns itself with what people call non-invertible symmetries. Now, I sincerely hope that I wouldn't be the first person to introduce them, but I think it only featured once very briefly so far. The simplest example for which we know is if you consider transverse field Ising chain, so this is 1+1 dimension, and the Hamiltonian could be taken to be, for instance, of this form, where you have a product of the Z operators, and I apply external magnetic field in the transverse direction. So there is a duality in this model such that when you increase H, as we of course well know, for large H, you end up in a trivial paramagnet phase. But on the left-hand side, you have two degenerate states. You could either have all the states, it's a cat state where everything points up, or all the spins point down in the basis that I've chosen. Now, which of these two states gets chosen is spontaneously chosen, and so this is an example of spontaneous symmetry breaking. Now, it turns out that this model is self-dual. That is, if I give you a Hamiltonian like this, there is a duality operator that transforms this Hamiltonian to identical form. And I'm going to write this down here for completeness. That would look like this. Yeah, that would work. Where I would have, I'll write this like this, tau x minus, and I will have, in this case, tau z operators, written like so. Okay, so this is my Hamiltonian over here, and what has which, right, sorry, I did it the other way around. Sorry, I meant to write down H here. Sorry, thank you. Okay, so you could think of this as that you think of H as being the external field. Another way to form it is that if I were to, there's another way of thinking about this, dividing both sides of the Hamiltonian and thinking of the coupling constants here and here. And what this does, it changes it or inverts it. So the phase diagram of this model would be the opposite. You would start from a trivial phase for small fields, and you will have a spontaneous symmetry broken phase for large fields. And since this duality preserves the spectra, and therefore the two states have to be correspondents to one another. Now, it turns out, and this was realized perhaps a long time ago, that this operator D cannot possibly be invertible. So what I mean by this is that you could see it by looking at the fact that here there are two degenerate ground states, and here there is only one. And you might wonder about how is it possible that the two states are mapped onto one another. And the answer is that the way to do it is to project one of them out. And the projection is something that you cannot invert. It's a non-unitary operation. Another way to state this is that if you look at exactly at the point where H is equal to 1, the fact that the model has this emergent symmetry, and hence the name of non-invertible symmetry, tells you that the spectrum has to somehow change from being two-fold degenerate to the one-fold degenerate. And that indicates that there has to be either an intermediate phase, or in this case, that it's a critical point. So the point actually becomes gapless. So to summarize, the operator D, this duality, is both non-invertible, is in the title over here, but it turns out it's also anomalous in the sense of quantum anomaly that we heard from Ashok in the previous 2 days. And it's the anomaly of that quantum non-invertible symmetry that protects these gapless points. That's a modern understanding of this. Now, historically, and that's why I said it's hard to put the date line, there is a famous paper going to 1949, which was written by Kramers and Vanier, who studied a classical two-dimensional Ising model. Now, from here, you could argue that it's almost what this is, because if you were to employ the classical to quantum duality, you could write down this 1+1 dimensional quantum model as a two-dimensional classical model. And for that reason, sometimes this is called a Kramers-Vanier duality. It's a bit of a misnomer. Certainly, Kramers and Vanier did not think about non-invertibility or quantum anomalies. For them, it was just a classical Hamiltonian, and they proved that the partition function on the left and on the right were equal to one another. So the duality was establishing, the correspondence between the corresponding phases. Yeah. So I would object to calling it a Kramers-Vanier, but since the majority of the community calls it Kramers-Vanier, this is a Kramers-Vanier duality. Question? The formal answer, and this came up circa 2022 from the work by Shuheng Shao and Nati Zeiberg plus others. And I should point out that much before that, around 2011, there was a work by Musinov and Ortiz, who also pointed out that if you have closed boundary conditions, by closed I mean periodic or antiperiodic, there is no way to write down this duality as a unitary operator. And in fact, what you could show is that the duality operator D could be written as a product of some unitary times a projection operator, and I'll talk more about this. Okay? So you could invert U, but you cannot invert the projector. Correct. Yes. Okay. So now, what I'm about, oh, there are questions. Okay, please go ahead, whichever order. Say it again, please. Yes. I am not sure if I can answer this correctly. I do not know. Frank? Yes. And I'll comment on this. Yes, yes, I absolutely agree with you. Yeah. No context here. Okay. So now, what I'm about to present to you is to unite these two objects, the one form symmetry that I described here with the non-invertible symmetries. Most of non-invertible symmetries that we know, or dualities, they work either in 1+1 dimension, or they're examples of 3+1 dimensions. A few mathematicians maybe, as Benoit was pointing out, what's the point of limiting yourself to any dimension, right? What we looked for is an example of being 2+1 dimensions, where to the best of our knowledge, there wasn't an example, at least that I knew of. And this allows me to introduce the model that I will use over here. I'll come back to this. And the model looks as follows. Let's take a square lattice. Unlike the toric code, my qubits or my sites, degrees of freedom, are going to live on the sides of the model. And allow me to consider the Hamiltonian H, which would be of this form. It's a sum over plaquettes. Let's take this plaquette over here, where I take a product. I'm going to switch to notation and call them sigma z throughout. And I'll swap the indices, but think of the sides 1, 2, 3, 4. This is 1, 2, 3, 4, and you sum over all of this. Okay? This is sometimes called Ising plaquette model, or you could see from here why it's called so. And this model has interesting properties. If you look at what are the symmetry operators that defined over here, they look like one-form symmetries, because what you realize is that I could define, if I look, for instance, in a given column, oh, sorry, it's a row. In a given row, I could define this operator, which would be the product of J of the sigma x operators with the coordinates ij. So think of this way, I take an entire row and I flip all the spins. What will happen? So let's say you started in a trivial phase where everything points up. So let's say my Ising degrees of freedom are plus everywhere. Now what I've done, I swap them, flip them everywhere over here, and now I have minuses, and everywhere else I will have plus. As you could see, this does not actually change the eigenstate, but doesn't change the energy of the state. And so therefore, it's a symmetry that commutes with the Hamiltonian. And in fact, if you look at how many of these there are, well, the number of I would go from 1 to Ly. And I could similarly define the column symmetry if I look from above. And I were to, I'll use a different color, you swap something like this. And you think of this being as the operator, and it also commutes with the Hamiltonian. And so for a square lattice of Lx times Ly, there would be this many. Now you have to be careful, because if you take a product of all columns and all rows, the result is identity, because all of them will appear twice in this expression. And so if you look at the number of independent constraints or symmetries that you have, you will have Lx plus Ly minus 1 symmetry. And so therefore, when you look at the degeneracy of the ground state, you expect it to be this much degenerate. Okay, so this is the ground state degeneracy. This is not a topological state of matter. I'm not putting it on a genus, on a torus, for instance. This is just an open square lattice. Okay? Now, notice, by the way, that I could also add a transverse field to this and have a sum over the sides. And obviously, all the x operators commute with this and this, so it's also a symmetry of the Hamiltonian. This model was studied by Senke Shrew when he was still a PhD student with Joel Moore. And if I remember correctly, this was 2004. And they realized that this model is also self-dual. So if I look at what the phases of matter of this model, what they look like, of course, over here, I will have a trivial phase, much like I had in the example of the Ising chain. But on the left-hand side, I could choose any of these ground states. Okay? So there would be some spontaneous symmetry breaking over here. But notice that the states, not the states, the operators that realize the symmetry, they define on lines. So in the language here, some people call them rigid one-form symmetries. So you could call this a rigid one-form symmetries. And in the context of fractal physics, they are often called subsystem symmetries, because what I'm selecting a certain subsystem, either horizontal row or vertical column, and this forms my symmetry. Now, it's rigid in the sense that, unlike toric code, I cannot wiggle these lines around. If I try to do so, I will create excitations that will not work. They will have odd number of minuses, and this would violate energetically the constraint. Okay? So the main outcome, I'll tell you what the result is that what we've shown is that this 2+1-dimensional model has the corresponding non-invertible symmetry, which is realized at self-dual point. So I'll put an extra S. So this would be S for the subsystem spontaneous symmetry breaking. And this spontaneously symmetry broken phase is dual to the trivial phase via this duality. And what we've succeeded in doing is to write down explicitly the form of this operator as a sequential quantum circuit. So for people who wanted to implement this on a lattice, you could. It's going to be complicated because you would have to span the entire lattice, but as Mikhail showed us today, depending on how you do it, this may not be a problem. To do it maybe on Sycamore quantum computing. Okay, so what do we learn about this? So what are the main things? So first, let me show you the naive way of how you could prove that the duality exists. So one way to see it, and this is what Shu and Moore pointed out back 20 years ago, is that you could think about the algebra that enters this Hamiltonian. I have two kinds of operators. I have sigma x, and I have a product of the plaquettes. Okay? And you could see that if I square this operator, it will be 1, and if I square this would be 1, and whenever they share a common side, they anti-commute. So I could try to come up with a new tau x, which would be given by the product of sigma z's, sigma z, and sigma z. And then I need a dual variable that would also somehow anti-commute with this, right? And the natural object would be to ask what would be the tau z, and the tau z would correspond to, in this case, let me see if I get this right. Yes. So you could see that what will happen is that this term over here will just be labeled by tau x. And conversely, what you want is that you want, in some sense, a product of 4 taus to give you the corresponding sigma x. Okay? Now, how do you do this? The easiest way, pictorially, it doesn't actually matter where you put them, but to think of a dual lattice. You could imagine that your tau degrees of freedom, I'll use a different color, these are my tau degrees of freedom, live in the center of each plaquette. They form a dual lattice, and maybe I'll do it like this. And I'm looking at the interactions like that. So you could see that for each dual lattice, there is a side sigma associated with this, and it's this side over here. And conversely, if I focus my attention on a given tau, it's surrounded by 4 sigmas. Okay? There is something interesting. You see, I wrote what tau x looks like. You could say, okay, Andriy, what about tau z? So I wrote a product of 4 tau z, but what about a single one? And this is what would make the people like Nati Zyberg unhappy, or generally people who deal with continuum theories. Because if you want this to work on a given side I, what you have to do is a product of all, let's see, how would I do it? If this has some coordinates, let's call them qx and qy, and you want to have a product and you want to do something like this. And this would be a product of sigma x. And this would be, well, yeah, like that, with I and j. So what this looks like pictorially is that if you pick a side, let's say this one, and you ask, what is the corresponding tau z operator? It would be given by a membrane that would stretch everywhere over here, right? I could have chosen, by the way, the sign to be less and start from the top left corner. It doesn't matter. It's up to convention. But for now, imagine that this is an infinite lattice. Okay? This is a membrane operator, and it reminds you of fractons. Remember when Vijay was introducing the fractons, he pointed out that you create a pair of fractons or quartet of fractons by acting with the membrane operator. So what I'm doing here is showing you how to create a single fracton, effectively. Right? So essentially what I'm doing, I'm flipping all of the plaquettes except for one. And the way to think about this is that I've created one fracton here, one somewhere at infinity far away, one over here, and one over there. Now, you would object and say, well, fractons are really truly defined in 3+1 dimension. This is not X-cube model. This is a two-dimensional model, and those objections stand. It's not a stable phase of matter in the sense that adding this transverse field would actually make my fractons not to be stable. But modulo that objection, if I were to set H to 0, it's a classical fracton-like model with immobile excitations. I could even create planons or linons, depending on how you want to call them. So for instance, if I were to act with the X operators in a given line, what will happen, so imagine I take this line, but instead of running it through the entire system, I terminate over here. What it will do is that it would create two fractons, one over here and one over here, and then the other one on the other end, one here and one here. Now, these excitations that live here and here, you could think of them as dipolar fractons, or you could call them a planon. And in this two-dimensional model, they can only propagate in one line without bending. Okay? So this brings us to the central results of what we've shown. And this is that in addition to showing you what the symmetry is, we've also looked at the corresponding defects. And the defects of the symmetry operators come in several flavors. Yes, Sergej. Schematically. If I were to write, so we have it in it takes about one full page of formulas. So if I try it, it'll take me a lot of indices, lots of copying through, but I can verbally or I can try schematically show what it is. Now let me advertise the results for this, but since you ask, maybe let's do it out of order. I'll talk about defects in a moment. Okay. So let's discuss about what is the operator that actually implements the duality. The general form of this operator would be as follows. Let me see why I can do this. Right, let me jump to the far board. And I'll leave this for this. So for this Shumor model, the duality operator that we've derived has this form. Now, the U operator is the promised unitary that you're asking me about. And it's nasty looking. It roughly looks like this. For simplicity, I'll show you how to do it on a geometry where I wrap it around the cylinder. So imagine that I have a cylinder of length Lx, but Ly stretches to infinity up and down. Okay. So the idea would be my quantum circuit would involve acting on the entire given row. I don't know, let's call it K. And what this is, it involves a product of control X between a site and a site above it. So there is some control X operators that sort of interlink and form something like this. So if I were to do it, I would have to, do it sort of in two steps, if you will, right? So this would be a two-layer code, and this would be CX operators. So after you've acted on a row of CX, you then do a bunch of Adamar operators. So formally, this U would look like, I'll just schematically say that it's going to be a product of CX operators. Then there's going to be a product of Adamar operators that would act, on all the sides in a given row. And then to top it off, you would have two control Z's, or products of control Z's. And this would only be in a given row K. And then the full U would be proportional to something, a product of K going from 1 to Lx U sub K. And I'm sweeping a lot of details under the rug. This control Z's, if I focus on one side, let's say over here, they actually act to the side above and the side diagonally to x plus y. And so they, in a clever way, they interlink this. And so you have a network that connects the different vertical sides, but also different rows. So it's messy. But the interesting part I want to focus is not actually the form of U, which is not that enlightening, I would say, but this object over here. That's where the non-invertibility comes from if you have periodic boundary condition. Now, somebody asked, is that true for open boundary conditions? So what we show explicitly in our work is that if you have open boundary conditions, you can actually implement this without any projector. As Frank was anticipating, if I were to consider all possible boundary conditions, then I don't need to invoke non-invertibility. So if you ask me, what is this P plus? The answer is slightly longer. And let me write down what this is. So there are, let me do it this way. I could give you two attempts on how to do it. The first attempt would be to say that what this operator is, I'll call it PT. It's a projector such that, I'll just do it, projector on periodic boundary conditions on all rows and columns. I could make it precise, it'll just take me a bit of time, but essentially think about a given row. I have a side 1 and I have a side Lx over here. I could say that if I were to consider sigma I plus Lx, the state would be given by sigma I plus Lx plus Ti in this x direction, where the Tix could be 0 periodic boundary conditions or 1 for anti-periodic boundary conditions. So effectively what I'm saying is that for each row and for each column, you could do the same. I would like to project on all the T's. So for all T's, I want them to be all 0. So in other words, what you're doing, you're saying that if you give me a state that is, let's say, anti-periodic, I'm throwing it away. Okay? Now you could see that this result would, of course, be non-invertible because the kernel of the operator is non-trivial. Now there's a problem with this, and the reason why I called it attempt number 1. The problem with this is that you can ask the question of what constitutes a symmetry. And usually what do we say? Well, we want the operator that commutes with the Hamiltonian, right? That's common knowledge. And we say, well, in order to be invariant and the unitary time evolution, I want my operator D to commute with the Hamiltonian, okay? But that's not all. If you look at the classical work by Eugene Wigner, the way the symmetry is defined is that, yes, it has to be constant of motion, but there is another constraint. Under no measurement can you reveal the symmetry. Because if you could, it wouldn't be a symmetry. So what this tells you is that in addition, so this is constraint number 1, constraint number 2 is that the symmetry action must preserve transition probabilities. So explicitly, what do I mean by this? If you give me any two quantum states, let's call them alpha and beta, the following should be true. If I take alpha and beta and I square it, the result should be the same as if I act with the duality operator on both sides and I square it. This is what I mean by transition probabilities. So if you look at the classical work by Wigner, and he was in some sense, the father of the group theory in physics. I mean, of course, it was known to mathematicians. What followed from here is that Wigner pointed out that if I were to choose D to be unitary, I would of course be happy, because now that right-hand side would act like something like alpha, and I would have beta, and I would have U dagger U, and hence the requirement that in order for this to be equal to alpha beta squared, what I need is that I would like this to be equal to identity modulo perhaps a phase. So I could pick up a phase, which unless you do interference experiment, you wouldn't notice. But the matrices U otherwise have to be unitary. Okay. So now, if you apply the same logic over here, you say, wait a second, how am I going to do it, right? If I just said that this is non-unitary operator, then it cannot be a symmetry. The way of how to do this, and this would be my attempt number 2 of defining the symmetry, and this is how we actually done it, is that there is a way out of this, but it comes at a price. So attempt number 2 is that you declare that this operator P, the projector, has to act not on physical degrees of freedom, but you must enlarge the Hilbert space and act appropriately on ancilla. So in the language of quantum information, this would be ancilla. So concretely, the way you would do this is often done by so-called half gauging or partial gauging procedure. Let me show you how it works in 1+1 dimensional case. I'll jump to that board over here. So the way it's done in 1+1 dimension was first shown by Nati Zyberg and Shuheng Shao to the best of my knowledge, at least explicitly. And the logic was this, that you define the operator by acting an extra link to this model. So what you do is that this goes from 1 to L, but you do something clever. You add an extra site, which would couple link ZL plus 1, and you minimally couple it in a gauge way. So you couple it to something like X on the side 1 and X on the side L. So what I've done is that if you imagine a one-dimensional chain, I'm thinking of periodic boundary conditions. If they're open, none of this matters. But if you have open boundary conditions, what I'm doing is that I'm saying that the side 1 is actually connected to the side L, right? So this is my periodic boundary conditions. And what I'm going to do is that I'm going to insert an extra site. Now, what is the purpose of this? This is my side ZL plus 1. It's an ancilla. It's a degree of freedom that wasn't there before. You see that the price that comes is that I have to work in an extended Hilbert space, which in this particular case happens to be the direct product of this extra ancilla times the Hilbert space of the original model. Or another way to say it is that I have 2 copies of the Hamiltonian. I have one where the ancilla in a 0 state, and I have another one where this ancilla, let's say, in a 1 state. I'm doubling the size of my Hilbert space in order to accommodate this ancilla. Now, just like in the spirit of measurement-based quantum computing, eventually I'm going to project out. I'm going to do a measurement on this ancilla. And that's exactly what the operator P plus does. So the requirement is that this D, which is U times P plus, but what P plus operator is, I could write it succinctly like this. What it does, it's P plus projects onto a state where ancilla is in a 1 state. And otherwise, well, I've chosen here Z that's equal to plus or minus 1, right? And otherwise, if it acts on a 0 state, the result will be 0. So it projects onto the ancilla being quote unquote in the up state. Okay? So this makes Wigner very happy, because if you look now at the states that appear over there, this projector operator acts trivially on the original Hilbert space. It only touches the ancilla. It doesn't touch the original code qubits. Yes? Well, not quite, because you see, one way to phrase it is this, what Frank was saying. If I consider all possible boundary conditions, that's saying that Z could be +1 or -1. So I haven't actually violating anything, right? I'm agnostic as to what it is. And so both spaces are included. What the projection does, it projects this on a particular state of H, let's say in a one state. Exactly, exactly. So the idea is that the states alpha and beta that I choose, they live in the original Hilbert space. They don't care about the presence of the ancilla. So it's pretty much in the spirit of, for those of you who think of quantum computing, of the idea of this introducing the ancillas as sort of the extra leg. And then what you do is that in the end, you project it out, if you will perform a projective measurement. Of course, that destroys the information of the ancilla, but doesn't touch your code qubits. Okay? So my watch says that I have 8 minutes to wrap this up. So as I said, that's fine. So the attempt number 2 essentially mimics what I've done here. And so the idea is that now it's the same unitary, but now this operator P plus that I've declared over there no longer does what's written over there, but instead this P plus contains the product over the ancillas. And this ancillas go something like from 1 to Lx, and there is Qx and Qy from 1 to Ly minus 1. And what this is, it's something very similar. It's 1 plus the corresponding Z at the corresponding Qx, Qy over 2. Okay? And these are my extra ancillas. Where they live is easy to show. So if I focus on a geometry that looks like this, these ancillas are inserted in some sense along, one edge. Or so essentially, this idea is that given some square lattice, let me go back to this. I give you a square lattice. Then I select a portion of it, some region in space, and I want to see where the states are. It's easiest if I do it like this with periodic boundary condition, I just extend. So this is going to be the region in which I do the so-called half gauging. And then my degrees of freedom, they will live everywhere around the edge over here. So this would be the ancillas that I need. And the length or the number of them, turns out that in order to do this, I have to insert them everywhere up to here. So in some sense, I'm covering the entire half space. And the ancillas live over there. And the numbers of these ancillas in total, there is Lx plus Ly minus 1 of them. And this number is not an accident. It's exactly equal to the number of subsystem symmetries that I have in the problem. In the case of a chain, I just had one symmetry. That was Z2 symmetry of the Ising model. I needed one ancilla. But in this case, I need more. So in the short time that I have left, let me tell you the summary of the results. You could ask about what are the defects of the corresponding symmetries. Okay? So I could introduce a fracton. And what the quote-unquote fracton is essentially acting with this membrane and leaving around essentially one Z that has been flipped. Okay? So that only affects one square, and that's my fracton. And if you were to act with two fractons which are next to each other, so imagine I have one fracton over here and one fracton over there, you could create this by acting with a string of X operators that goes all the way from a given side. So let's say this is a side Q. So this would be what people often call eta in a given row. And if you ask me what it corresponds to, the corresponding operator would be like a product for I larger than Q of sigma X of I in a given row. Okay. So I'm not putting indices and I'm being a bit cavalier here, but essentially the product or the fusion of the two fractons gives you an eta defect. You could also fuse the fracton obviously this way, and this would be the defect that extends all the way down. So you could also say that this is like fractons in a horizontal manner, and there's a fractons in a vertical manner. Remember when Julian told us earlier about how you count the objects in your category? Metamorphing, here you have to be careful because the fractons depend where they are. if I give you one fraction over here and another fraction over there, I can't claim that I can do this, right? So it's only when they're nearby. Since the system is translation invariant, often what we say is that I can always move this up to here. And by moving, I have to act with some membrane operator. So once I move them, I can fuse. So that's my 5 minutes. Okay. So I can fuse them, and that gives me the eta defects. Okay. Now, I could also take two eta defects and show that eta cross eta would give me identity. So that tells me that if I take two strings, I could sort of annihilate them if I trivially, combine them. But you have to be careful because this eta could be horizontal, or there could be eta that's vertical, and they're clearly distinct. Okay, so I have several kinds of defects. The most interesting is the fusion of the D defect. So remember, D is a symmetry. What do I mean by a fusion defect? I take my system, let's say a cylinder. Let me see how I can use this. So let's say again, I come back to my symmetry. I take a D defect, and what I do, I do a dual model. So let's say if this model is a Hamiltonian with some field H, here I will have a Hamiltonian which is dual, where H and H inverse got changed. And then I have another defect over here, and on the right of it, I have again the original Hamiltonian. So what do I mean by fusing these defects? I have one defect here at some position I. I have another defect at some position I prime. I move them next to each other and I quote unquote annihilate them, and I see what happens. Okay? So if you look at it from far away, so to speak, you could ask what is the result of this fusion? And it turns out that the result of this fusion is non-abelian, in a sense as was described by Julian, in a sense that the outcome is either a vacuum or you have an eta. But if you ask me what this eta is, it's a strange object that has the strings that live in every single, they span the entire cylinder, kind of going like this. So I will have eta horizontal in each of them. So in some sense, this eta is like a combined operator that includes all of it. Now, remember I asked Benoit, what do you mean by a plus sign? Well, I asked Julian and Benoit answered. You see why I was worried about this? Because this is a bona fide operator, fusion operator, that acts on the Hilbert space. And so now what do I mean by this? And in my case, the answer is the following. If I were to decode expressly what is actually meant here, the answer is that my Hamiltonian, my Hilbert space has been enlarged. So this operator H, there are some auxiliary degrees of freedom that are introduced that live everywhere, let's say over here. These are my extra ancillas. And so what I have to do is that, this idea is that this is like a original Hilbert space where all the states are in a zero state. And then this plus is actually more complicated. So more strictly speaking, what I should be writing here is something like direct sum over all the rows, so from Y to Ly. And for each of them, I have 1 plus eta in a given row. And this is a direct sum in the sense that in each of this, what I'm dealing with is essentially, how should I say, the right-hand side of this is a original Hamiltonian times, I'll do it like this. Let's say all my ancillas are in a zero state, which is trivial, plus, sum over all from 1, I shouldn't just 1, 2 to the power L minus 1. I will have many different defects. For instance, I could have this one have the eigenvalue of +1 and the rest of them -1. And there is 2 to the power L of different combinations. When they're all flipped up, that's precisely this first term, right? And then there is a bunch of all the other things. And the number of terms in the sum is 2 to the power L minus 1. And this P plus operator that I declared over there, what it does, it precisely takes all the ancillas and puts them in a zero state, right? Projects them out. And that's the sense in which it's non-invertible operator. So you could see if you're interested, you could see more of these details in the two papers on arXiv. What I didn't have time to tell you about is the work that was done by Avijit Maiti. So he's in the audience and he's working at TIFR. He's a graduate student about to graduate. So what was done with Avijit was to show that this quote-unquote Kramer-Svania, really not Kramer-Svania, but you know what I mean, the duality in this sense, that it can indeed be shown to be invertible if I have open boundary conditions. It's non-invertible if I have closed boundary conditions. And it's not enough to say periodic or antiperiodic, because for each row and each column, I could individually choose this to be periodic or antiperiodic. So there is a total of this many 2 to the power Lx plus Ly minus 1 different twist sectors. That's exactly the number of states in the Hilbert space of the ancillas that I need. And I'll finish, if you give me just 2 more minutes, on a sort of more general, maybe field theoretical notion. What Kramer-Svania duality in 1+1D does, you could think of it in this way. It connects a spontaneous symmetry broken phase, or in our case, there is an extra S because it's subsystem symmetry. And what it does is that it connects this to the trivial phase. Okay? But there is another consideration. In phases of matter, we know that in addition to topological order, there is something called an SPT, symmetry-protected topological order. And so it turns out that there is another set of transformation that can transform a trivial state into SPT and can exchange an SSB with an SPT. And this forms the so-called web of dualities. So this transformation, often called domain wall decoration, the name is kind of historical. But the one I want to accentuate is the horizontal one. So what it tells you is if you give me a group, something that defines a symmetry, let's not worry about non-invertible ones for now, then there is a way to show or connect, to make a duality between a spontaneous symmetry broken phase and the SPT with a corresponding number of degenerate edge modes. Okay? This first was done explicitly for one-dimensional models, and this goes back to the story of Affleck, Kennedy, Lieb, and Tasaki, the famous AKLT states. Can you, by show of hands, tell me how many of you know what AKLT is? Okay, so I'd say about 2/3 of the audience. I'll be brief. I'll just tell you what the result is. So, of course, all of you know about Haldane conjecture, right? Afterwards, maybe, Benoit, you tell me why it's called conjecture, not a theorem. But anyway, what Haldane famously showed, and nobody believed him initially, by the way, is that the spin 1, or generally the integer spin chains, have a gapped ground state. Okay? And that's to do with the presence of a topological theta terms, and the story is well known by now. Okay? So if you do DMRG on a finite chain, and you look at the spectra of what you get, you will find that in addition to the ground state, which is, the one that's separated by a gap from everything else, according to Haldane, so this is a Haldane phase, there is something else. There are 3 states, a 3-fold degenerate excited states that are exponentially close in energy to the ground state. And that exponential closeness, or near degeneracy, was pointed out first by Kennedy, the same Kennedy as K in AKLT. And this is called a Kennedy triplet. And people for a while struggled to understand what the heck is going on. Why do I have this near degeneracy? And as you make my chain longer and longer, this becomes 4-fold degenerate. And there is a notion that actually there is a Z2 cross Z2 global symmetry, but the symmetry is somehow hidden. Like it's not obvious when you look at the Heisenberg SO3 symmetry of the spin 1 chain, like what the heck is this? Is it some sort of subgroup of the continuous Lie group? What does it actually mean? And it wasn't until, what was it, maybe 2008, where Xiaogan Wen and also the group of Masaki Oshikawa and Frank Polman pointed out that the modern understanding of this is that this is an SPT phase, and the Z2 symmetries could be understood on a lattice. It's certain reflections around the bond centers, and I could go in more details, but the point is that we understand how this works on a lattice, what the symmetries actually are. But what they correspond to is that the ground state of this model is fourfold degenerate. So explicitly, if you take a finite chain, a KLT construction would show you that there would be some decoupled edge modes with two spin half that are kind of orphaned. And the spin up could point up or down, and this spin up, spin half could point up or down. And that's how you get the fourfold degeneracy of the edge states. This edge state is exponentially localized. Now, finally, I'm coming to the punchline and then I finish. What Kennedy then did, he and Tasaki wanted to make this symmetry explicit. And so a long time ago, I think it's like 1993, they pointed out that they could construct a duality that explicitly takes this hidden symmetry that nobody at the time knew where it comes from and makes it explicit, meaning you get a Hamiltonian, which is extremely simple, which has explicit system. And the way you do it is that on each spin half, spin one, you separate it into two sides. You call it sigma and tau. And under this duality, the Hamiltonian that is dual looks very simple. It's just a sum of all the sigmas, sigma z, sorry, it's a sum, plus a term, which is tau iz, tau iz. It's like all taus only interact with one another, and all sigmas only interact with one another. And of course, here you have a twofold degenerate ground state. They could all point up, or they could point all down, and the same could be done for taus. And so this was very instructive. It was an explicit mapping. It was non-unitary if you have closed boundary conditions, but it's some strangely non-local transformation. It involves string nets, not string nets, sorry, a string order parameter. But what it does, it shows you how an SPT with this hidden symmetry is connected to spontaneous symmetry broken in a phase which is extremely simple. It's an Ising phase. So finally, what we've succeeded in doing is doing the same for the Schuh-Mohr model. So for this system, for this 2+1-dimensional system, we've shown that there is an equivalent of Kennedy-Tasaki-like transformation that takes this 2 to the power Lx plus Ly minus 1 degeneracy, which is an explicit degeneracy, and maps it on SPT. And this SPT has the exact same number of, if you will, degenerate strong edge modes. And for the experts in the audience, this goes under the name of strong SPT. In 2 dimensions, there is a distinction between weak and strong. And interestingly enough, it maps on the so-called 2D cluster state. And in his talk, Michal pointed out that you could achieve the ground state of a toric code by doing measurements on the so-called cluster states. That is the same cluster state as we've derived over here. So there are some deep connections, and we show it in the paper, but I should stop. Thank you.
Any quick questions? Yes.
Yes. Or in this case, right, so the model we consider has Z2, yeah, I should be more concrete. So this model that's here is Z2 cross Z2 subsystem symmetry. Okay, so I need 2 copies, just like I had sigmas and taus over here. I need kind of 2 copies of the Schuh-Mohr model to make this work. You could think of them in some sense as a combined spin ones, but yeah. No, so in the original formulation, what you do is that you project the state of sigma and tau onto S equal 1 state, right? So in other words, you take representations of the SO3, SU2 in this case, and you choose this state over here. You project onto 1. This is close to how MPS are, right? So when you form an MPS, you have a bond degree of freedom. So think of sigma and tau as being the dimension of your bond. And then physical degree of freedom is spin 1, right, which sticks from each tensor that sits over here. And you demand that the physical space is, is threefold. The Hilbert space on site has 3 states, and you throw away the 0 state.
Okay, maybe we can close the session. Let's thank Andriy again, and please catch hold of him. Thank you.